Next up, Emma Wierma is going to give us a great overview video, take us on a tour of some facilities and some actual species. So, all right, Emma.
Thank you, Titus, and thanks everybody for joining us today. So to mix things up a little bit, I created a video for this presentation. So the video was created specifically for this Great Lakes Aquaculture Day to show you some very basic overview of aquaculture systems and see some of these systems in action. Special shout out and thank you to all the farms that are showcased in this video, as well as the various extension and educators that provided additional media and support. So the video is about 16 minutes in length. If we don't have time for questions, there's contact information at the end of this video. Please jot that down. You're welcome to contact myself or any of our staff here that is portrayed in the video. With that, big thank you to the communications team for setting this up, and you are welcome to go ahead and play it. Thank you.
Today we will be explaining some of the basic aquaculture systems. These systems shown in the video will include research and demonstration systems at the University of Wisconsin Stevens Point Northern Aquaculture Demonstration Facility, or UWSP-NADF. The UWSP-NADF is a remote campus of UW Stevens Point, located about 4 hours north of the university in Red Cliff, Wisconsin. The facility's mission is to promote public education and advance the discovery, dissemination, and application of knowledge for sustainable aquaculture in a northern climate. The facility is one of a kind in the Midwest and joins only a handful in the nation that offer the variety of species and life stages, systems, training and educational abilities, and semi-commercially scaled research applications. The success of the facility is directly due to the experienced and knowledgeable facility staff. Understand that we are a resource to you. Contact information will be provided at the end of this video. To begin our overview of aquaculture systems, there are a few key concepts to remember about any system used for aquaculture. Systems must efficiently meet the biological requirement of the species raised regarding things like water quality, flow rates and velocity, and environmental aspects. The system must meet the economics of the business plan, things like capital, electric, permitting, labor costs. And the system must also be in a correct location. Location in terms of markets, land use, topography, climate may make sense for some systems, while not others. In addition, another very important concept is, of course, water. We refer to this as water in and water out. For the incoming water into your system must meet biological requirements of the species raised and also maintain biosecurity, groundwater being the most biosecure. Water out in terms of effective solids removal from your system, as well as the discharge and effluent regarding permitting or regulations. Aquaculture systems can range from low intensity to high intensity. In general, as systems increase in this intensity, annual production is also increased, shown in this diagram. As you can see, there is a variety of systems mentioned in this diagram. We will be highlighting only the basic types: ponds, raceways, recirculating, and aquaponics systems. To begin, we will first describe the pond system. Ponds can be used to raise a variety of species. Although cool to warm water species such as bass, walleye, yellow perch, and panfish are common due to the increasing temperatures of ponds in the summer months, which will generally not support cold water species. Ponds are appealing due to several reasons. For one, fish are generally raised at lower densities than other systems, which can potentially lead to lower stress, faster growth, and lower transmission of disease. Ponds contain effluents or waste in one location until the pond is dredged or drained, making permitting sometimes easier than a flow-through system. Ponds may also have somewhat of a buffering capacity for operational mistakes, making them a good starter system for beginners. Lastly, ponds are currently the most economical system on a global scale. Ponds require a large land area and available water. Fish often show seasonal growth in winter climates, and there is an increased risk of fish predation and biosecurity. Ponds may also require adequate oxygen for fish to survive and thrive. This generally requires use of electric aerators, diffusers, or paddle wheels. Regarding types, there are two main categories of ponds, those that are natural and those that have been constructed. Natural ponds are large existing bodies of water that are generally permanent and non-drainable, making them difficult to harvest. In comparison, ponds that are constructed are generally a multitude of smaller, more manageable ponds which are manually filled and may be drainable for a complete harvest. Ponds may need to be lined with a material such as plastic or existing clay, which can be utilized in locations with soil consisting of over 20% clay content. To show you an example, NADF has 4 half-acre clay-lined ponds, which can then be drained individually into a collection kettle for complete harvest. The fish are netted out of the collection kettle, weighed for quantification, and then either placed onto a truck for stocking purposes, or they are backstocked into another pond for continued rearing. The facility has raised a variety of species in these ponds throughout the spring and summer months, with a current focus on walleye for stocking. For more information, a complete facility pond video module is available on our website, aquaculture.uwsp.edu. Our next system we will discuss is raceways or flow-through systems. In these type of systems, water enters on one side of the system, passing through the fish and exiting at the other end. Because of the continual water replacement, cold water fish species are generally utilized in raceways, such as trout and salmon. Raceways are considered one of the earliest types of inland aquaculture systems. These types of systems are utilized at many federal, state, and tribal hatcheries, as well as older farms and facilities in our region. They are also commonly found where water is plentiful and topography is suitable. Raceways should be situated near an adequate water supply with appropriate discharge as well as topography to enable around an 8 to 10% slope. Some benefits to raceway systems include continual flow of water, which is replacing the oxygen and maintaining temperature while removing ammonia and carbon dioxide. Generally, raceways support higher density of fish than a pond system, with lower concentration of solids and nutrient buildup in the system. Harvesting, feeding, and grading fish are generally more efficient and easier than in a pond system. In contrast, some challenges to raceways include utilizing a large volume of continuous replacement of water, difficulties in cleaning, and difficulties in removing effluent waste from a high volume of discharge. These challenges may lead to additional permitting costs and regulations. There are a variety of raceway types, including parallel, which water flows through a channel once and is discharged, as shown here at NADF, or in series, where water flows through multiple raceways, which is the most common method. In a series, before water continues to the next raceway, oxygen generally needs to be replaced by use of a cascading design, where water drops about 18 to 24 inches before the next raceway, or use of oxygen supplementation, such as low-head oxygenators. Another flow-through type may include floating raceways that float in existing bodies of water. The water still enters at one end and exits the other end of the raceway. The next system we will highlight is recirculating aquaculture systems, or RAS. Due to the complexity of RAS equipment and technologies, we will be going into the most detail with this type of system. Also, some of the concepts in RAS can also be applied to aquaponics systems discussed next. One of the greatest advantages to RAS is increased optimization and control for parameters such as water quality, temperature, and other environmental aspects of the tank, making these systems highly species adaptable, with predictable harvest, survival, and biosecurity. Advancements in RAS technology has enabled designs that can meet the biological requirements of specific species, providing an optimal environment for a variety of aquaculture species from walleye to Atlantic salmon. These systems can also be more environmentally sustainable when considering conservation of heat, land, water use, and low impact to surrounding environments and effluent management. These systems can range from a partial reuse system to reuse of nearly 99% of the system water. The intensity of these systems also poses several challenges, including costs in design, equipment, electricity, and labor. These systems also require specific expertise and training to run and manage, as well as incorporation of crucial monitoring, alarm, and emergency capabilities 24/7. Economic and business planning are very important concepts to the success of RIS systems, which also includes choosing a profitable and marketable species to raise. The complexity of RIS requires specialized design by experienced engineering firms that will factor in the specific needs of the operation. Designing and operating RIS requires solid understanding of the following: mass balances, culture units, solids capture, nitrification, gas transfer, fluid mechanics, waste management, feeds and nutrition, biosecurity, systems monitoring, and building heat and moisture control. In this video, we will describe the very basic processes involved in an RIS using UWSP NADF equipment as examples. Understand that there are a variety of different equipment and different designs that can be utilized. Generally, the first process in RIS is solid concentration and removal. Starting in the fish tanks, UWSP NADF utilizes tanks with two drains, known as Cornell-style dual drain tanks. The cleaner water that leaves the tank comes from the side drain, about 90% of the tank outflow. Most of the solids, such as the feed and fecal material, flow out of the bottom drain, which is about 10% of the outflow. In this system, the bottom drain flow is sent to a radial flow settler, which further settles out these solids. By opening a valve, these solids are sent to the facility's settling or clarifying pond, along with the other outflow leaving the facility. The side drain is sent to a micro screen drum filter, which mechanically removes the lighter suspended solids. The micro screen comes in various sizes depending on the system and application. The next process to discuss is biofiltration, in which supports the nitrification process or the removal of both ammonia and nitrite, both very toxic to fish at low levels. This process is accomplished by various types of beneficial bacteria living in a biofilter. The key to biofiltration is allowing for a high amount of surface area for the bacteria to live on. There are many different types of biofilters, including this fluidized sand biofilter shown here, where the water is pumped from the bottom of the filter and fluidized up through the sand. Another type is a moving bed bioreactor, which uses media such as Caldness media to provide surface area. The media is in constant rotation here due to the addition of aeration. Another process of RIS involves degassing. The system water gravity flows through a degassing column of packed media, releasing harmful gases such as carbon dioxide, which is produced by the fish. Makeup air units and fans inside the facility ensure that this carbon dioxide is removed from the building and fresh air is brought in. Sterilization is also an important process in RIS, which uses equipment such as ultraviolet irradiation, ozone, or both to disinfect the water of pathogens or viruses before returning to the fish. Finally, the water is re-oxygenated before returning to the fish tanks. Equipment examples include oxygen cones, which inject oxygen under pressure. These are typically needed for warm water systems. Another method is utilizing a low head oxygenator, where water gravity flows through a series of high oxygenated panels and are typically used in cold water systems. These processes are the basic concepts and examples of equipment involved in RIS. Again, effective systems are specialized and designed by experienced engineering firms to meet the needs and application of specific facilities. The last system highlighted today will be aquaponics. As with all these systems mentioned, there is a variety of designs and equipment involved in aquaponics. In a general sense, aquaponics is a type of water reuse system in which the waste generated by the fish is utilized as nutrients for plant production. These systems can be coupled, where all the water is sent to the plants and then back to the fish, or decoupled, where the plant and fish systems are run independently of one another. Decoupled systems consist of an independent recirculating aquaculture system, which sends a smaller stream of more concentrated nutrients to the plants. This water may or may not return to the fish. Plants can be raised in a variety of different ways in aquaponics. Some examples include floating raft, nutrient film technique, or within media beds. Although pros and cons to each, they must all provide adequate micro and macronutrients as well as oxygen to the plant roots. Aquaponics systems can be quite basic to highly complex systems, utilizing equipment mentioned previously in recirculating aquaculture systems. One important step to aquaponics that was not described in an RAS is mineralization, where some of the solids are mineralized to release micronutrients that are important to plant production. Beneficial bacteria, described within the biofilters of an RAS, are also key players in aquaponics. Aquaponics requires expertise in both plant and fish production, as well as understanding the concepts behind recirculating aquaculture, such as nitrification and biosecurity. Unfortunately, there has not been much research published on aquaponics with species other than the typical tilapia and lettuce in a coupled system. The UWSP NADF recently investigated raising walleye to market size in an aquaponics system as well as in RAS, comparing various densities and nutrient recycling of each system. Data is currently being analyzed for the study. The published results will also include biological and economic models for walleye produced in these systems. Thank you for your attention. To wrap up, I'd like to provide some contact information for our staff. Dr. Chris Hartleb for information on UWSP aquaculture and aquaponics education opportunities. Greg Fisher if you are looking for specific facility research questions, technical expertise for various systems or species. And Emma Wierma if you have general questions regarding aquaculture resources, tours, or K-12 education opportunities. Further information on facility projects, deliverables, and additional resources, please visit aquaculture.uwsp.edu.
All right, thank you, Emma. That was fantastic. I think we're going to all enjoy that, watching that video over and over again in the future.